Concentration is a general term that expresses the quantity of a solute contained in a given amount of solution. Various ways of expressing concentrations are in use. The choice is usually a matter of convenience in a particular application. You should become familiar with all of them. After this model, you should be able to calculate the concentration of a solution in terms of molarity, molality, mole fraction, percent composition, and parts per million, and be able to interconvert between them. The most common units of concentrations are mass percentage, parts per million or ppm, parts per billion or ppb, mole fraction, molarity, and molality. The mass percentage. Percent means out of 100. Take the ratio of the mass of the solute and divide it by the total solution of the mass. Then multiply by 100 to make it a percent. In other words, the mass of the component or the solute will be equal to the mass of the component in the solution or the mass of the solute in the solution divided by the total mass of solution times 100. Remember that the total mass of the solution will be equal to the mass of the solute plus the mass of the solvent. Let's see the following example.
Let's do this example. A solution is made by dissolving 13.5 grams of glucose in 0.100 kilograms of water. What is the mass percentage of glucose in this solution? So the mass percentage of glucose for this solution will be equal to the mass of glucose divided by the mass of the solution. This time 100 because it's percentage. But what is the mass of the solution? The components of the solutions are what? Are glucose and water. So that means that this is equal to the mass of glucose divided by the mass of glucose plus the mass of water, H2O times 100. Now, if we can see here that we have the mass of glucose in grams, but we have the mass of water in kilograms, and we need to have both units the same. So let's change the kilograms of water to grams of water. So we have 0.100 kilograms of water, and there is a conversion factor that says that 1 kilogram of water is equal to 1,000 grams of water. So now we can cancel the units of kilograms, and we now have the units in grams of water, and this will be equal to 100 grams of water. So now we can substitute the values here. So the mass of glucose is 13.5 grams, 13.5 grams of glucose divided by 13.45 grams of glucose plus 100 grams of water times 100. And this will be equal to 11.9% of glucose. So this is the mass percentage of glucose.
The next units are parts per million ppm and parts per billion ppb. Still relating the mass of the solute to the total mass of the solution. Since percent is out of 100, we multiply by 100. ppm is per million, so we multiply by 10 power of 6. ppm of a component is going to be equal to the mass of the component in the solution divided by the total mass of the solution times 10 power of 6. ppb is per billion, so we multiply by 10 power of 9. So let's see the following examples.
A solution with a relatively small concentration of solid is said to be dilute. It is very common for those type of solutions, diluted solutions, to have the units of parts per millions or parts per billions, ppm or ppb. In this example, we have a 2.5 gram of sample of groundwater that was found to contain 5.4 micrograms of zinc 2 plus. What is the concentration of zinc 2 plus in parts per million? As we remind, ppm, it's equal to the mass of the solid divided by the mass of the solution. And this is multiplied times 10 power of 6. Now, we need to find, because we're looking for ppm, we need to find the mass of the solid and the mass of the solution, and we have both of them. But the only thing is that we have the units of gram in the sample of the solution and of microgram in the sample of the solid. So we need to change the units of the solid, 5.4 micrograms of zinc 2 plus, and we're going to use the conversion factor of micrograms to gram. Remember that 1 microgram is equal to 10 power of minus 6 grams, or 1 gram is equal to 10 power of 6 microgram. It doesn't matter which one to use. So we're going to use here that 1 microgram of zinc 2 plus is equal to 1 times 10 minus 6 gram of zinc 2 plus. Let me write a plus here. Okay, there you go. Now we can cancel the units of micrograms of zinc, and this will be equal to 5.4 times 10 of power of minus 6 grams of zinc 2 plus. So now we have the mass of the solid and the mass of the solvent. So we go again to the formula. ppm will be equal to 5.4 grams, 5.4, sorry, times 10 minus 6 grams of zinc 2 plus divided by the mass of the solution, that is 2.5 grams of the solution, times 10 power of 6, and this will be equal to 2.2 ppm of zinc 2 plus.
The next unit is mole fraction. The mole fraction is the ratio of moles of a substance to the total number of moles in a solution. It doesn't matter if it is for a solid or for a solvent. So the mole fraction of the component, this could be the solvent or the solid, will be equal to the moles of the component divided by the total moles of all components. So in other words, if we want to find the mole fraction of the solvent, it will be the moles of the solvent divided by the total moles of the components. If we're looking for the mole fraction of the solid, it will be the moles of the solid divided by the total moles of all components. Let's see the following example.
A solution contains 36.5 grams of HCl and 144 grams of H2O. What is the mole fraction for HCl and for H2O? So as we remember, the mole fraction is equal to the moles of the component divided by the total moles of the components of the solution. Okay, so if we want to determine the molar fraction of HCl, this will be equal to the moles of HCl divided by the moles of HCl plus the moles of water, because the solution is HCl and water. So if we want to determine also the fraction mole of H2O, this will be equal to the moles of H2O divided by the moles of HCl plus the moles of H2O. So how can we determine the numbers of moles? How can we determine moles? So we have, instead of moles here, we have the grams of each of the components. So we need to look for the moles of each of the components. So how can we turn, or we change the units of gram to moles? Using what? Using the molar mass. Okay, so the molar mass for HCl will be equal to 36.5 grams per mole, and the molar mass for H2O will be equal to 18.0 grams per mole. Now to determine the moles of HCl, we need to start with the grams of HCl. It was 36.5 grams of HCl, and we have that 1 mole of HCl is equal to 36.5 grams of HCl. So now we can cancel grams of HCl, and this will be equal to 1 mole of HCl. Now for the moles of H2O, we start with 144 grams of H2O, and the same way we know that 1 mole of H2O is equal to 18 grams of H2O. So now we can cancel grams of H2O, and 144 divided by 18 is going to be equal to 8 moles of H2O. So here we have the moles of HCl and the moles of H2O. So the molar fraction, let me look for this, of HCl is going to be equal to 1 divided 1 mole of HCl divided by 1 mole of HCl plus 8 moles of H2O, and this will be equal to 1 divided by 9, and this will be equal to 0.111. That's the mole fraction of HCl. For water, the molar fraction for water will be equal to 8 moles of H2O divided by 9 moles total. And this will be equal to 0.889.
The last two units of the solutions are molarity with capital M is represented by capital M molarity and molality that is represented by lowercase m. Molarity was discussed in chapter 4 as moles of solid per liter of solution. So molarity is equal to the moles of the solid divided by the volume of the solution, in this case in liters. The molality is moles of the solid per kilogram of solvent. So molality is equal to the moles of the solid divided by the kilograms of the solvent. Molarity versus molality. When water is the solvent, dilute solution have similar molarity and molality. Molality does not vary with temperature. Mass does not change. Molarity varies with temperature because the volume changes. Let's see the following examples using the molarity and the molality units.
Let's give an example of how to calculate the molarity of a solution. This solution is made by dissolving 4.35 grams of glucose in 25 ml of water. So, the molarity is equal to the moles of the solid divided by the liters of the solution. So, in this example, we can calculate the moles from the grams of glucose, and we can calculate the volume from the volume of water that we have. Okay, so let's work first with calculating the moles of the solid, and this will be equal to 4.35 grams of glucose. So to change from grams to moles, we need the molar mass, and the molar mass of glucose is 1 mole of glucose will be equal to 180.2 grams of glucose. So now here we can cancel the grams of glucose, and now this will be equal to 4.35 divided by 180.2 to 0.0241 moles of glucose. Now, for the volume of the solution, we have 25 mils. We need to change to liters of H2O. So in 1 liter of H2O, we have H2O. We have 1,000 milliliters of H2O. This is a conversion factor. And now we can cancel the units of the mils of H2O, and this will be equal to 0.025 liters of H2O. That is the volume of the solution. So the molarity will be equal to 0.0241 moles of the solid divided by 0.025 liters of H2O, and this will be equal to 0.964 molar of glucose. So let's work this example of how to calculate the molality of a solution. This one is made by dissolving 8.0 grams of sodium hydroxide in 500 milliliters of water. So
the molality is equal to the moles, in this case of sodium hydroxide, divided by the kilograms of the solution. So, from the information that we have in the instructions, we can calculate, for example, the moles from the mass of the solid, that in this case is sodium hydroxide, and we can calculate the mass of the solution by using the data of 500 mils of water, okay, because water is basically the volume of the solution. So let's start first by working with to calculate the moles of sodium hydroxide. How can we calculate that? So we have here 8.0 grams of sodium hydroxide, and to change the units from grams to moles, we may need the molar mass of sodium hydroxide. In 1 mole of sodium hydroxide, we have 40 grams of sodium hydroxide. So that means that from here we now can cancel the units of grams, and we have our value in the units of moles. That is the one that we need. So 8 divided by 40, this will be equal to 0.200 moles of sodium hydroxide. Now we need to calculate the kilograms of the solution. Kilograms of the solution. And what we have first is 500 milliliters of H2O. So we have a volume unit here that we need to change to a mass unit because we want to calculate the kilogram. So what can help us to change from the volume to mass is the density. And we know that the density of water is 1 gram per mil, so 1 gram of water over 1 mil of H2O, 1 milliliter. So now we can cancel the unit of volume of milliliter of water, but we need to find out how many kilograms, because we have this in grams. So now we can change that unit of gram to kilogram by saying that in 1 kilogram of water we have 1,000 grams of water, because the conversion factor of kilograms and grams is 1 kilogram is equal to 1,000 grams. So now we can cancel the units of gram of water, and we have our unit of kilogram. So this will be equal to 0.500. Let me rewrite that again. Sorry for that. Here we have a 500 kilograms of water. Okay, so now we have moles and water. We have the moles of NaOH and the kilogram. So now the molality will be equal to 0.200 moles of sodium hydroxide divided by 0.500 kilograms of H2O, that is the mass of the kilogram of the solvent, and this will be equal to 0.400 molality of sodium hydroxide.